This week's lesson deals with a topic called evolution of stars. Just like you, stars also have a birth and they do have a death, and lots of other time in between, obviously. The lifespan of stars can stretch several billion years. So that's obviously much longer than human lifespan. But let's get into what this is then. Before we get to the actual life cycles, first part or the first slide really deals with something called the HR diagram. So there are these two astronomers. Their last names were Hertzsprung and Russell. And what they were trying to determine is, could they classify stars? Being scientists, as scientists, we like to classify things to try to make order of the universe. So they were interested in whether or not stars fit into certain categories. So they looked at basically just two characteristics. They looked at star temperature and they looked at magnitude or brightness. And they were given credit for looking at more stars than any other scientist. And what they found out was that, yes, stars actually do fit into certain categories if you look at their temperature and their brightness. And what they discovered is that 99% of all stars fit along this diagonal band. It's called the main sequence. Our sun happens to be a main sequence star. So this is the category that basically all stars exist in, main sequence stars. Some of them are extremely hot. You can see they're up at this end. This is the hot temperatures. Some of them are very cool. They're down at this end. But yes, most stars in the universe are main sequence stars. There are some stars that fit outside the main sequence. There are giants and supergiant stars like Antares and Betelgeuse. And then there are stars that are on this side of the chart, white dwarfs and neutron stars. What makes them different or lie outside the main sequence? Well, you can see white dwarfs and neutrons are extremely small stars, not very bright because they're down on the chart, and the lower in the chart you are, the dimmer that you are. But they are extremely hot. You can see they burn at really high temperatures, as opposed to giants and supergiants that are very cool stars because they're at this end of the spectrum. They're on this side of the chart, but they're also up really high on the chart, which means their magnitude is really, really bright, basically. All right, let's get into star evolution then. All stars are based upon a couple of different things: temperature, composition. The color of star really indicates its temperature, and you kind of saw that on the HR diagram. The blue whites, they were the extremely hot ones. Our yellow sun, yellow and orange are kind of the mid-temperature stars, and then the red stars are kind of the cooler stars. So how do scientists know this? It's not like we have gigantic thermometers that shoot out into space to these stars that are hundreds of millions of light years away. Well, basically, we study wavelengths. Wavelengths of light are used to look at the elements that make up stars. Now, how that's done, that is a deeper concept in physics that you'll get to when you get to physics at the high school. But just realize that we study wavelengths, or the colors of the rainbow, basically, Roy G. Biv, which is basically what the colors of stars are. Oh, and I did forget to mention that. If you've ever looked up at the nighttime sky, you think, boy, I've never seen a blue star, or I've never seen a green star. Well, that's because those stars are so far away that all we see from our vantage here on Earth is the fact that it's just a blending of light or white light. If you had a powerful enough telescope, though, you would be able to see that stars are made up of all the different colors of the rainbows: the reds, the orange, the yellows, the greens, the blues, the indigos, and the violets, basically. So that is true. All right, so all stars are born from nebula gas. Nebulas are clouds of gases and dust that basically stars form from. And when stars first form, they are main sequence stars. So this picture is actually a picture of a galaxy that you're looking at. So you're not actually looking at one star here. That's probably a cluster of hundreds of thousands of stars that are very close together, that make up this whole galaxy. And you can see this galaxy has a bunch of different color stars. I can see reds, the oranges, the blues, the violets, the whites that exist within that particular galaxy. So stars will be main sequence for billions of years. Our star, our sun, is thought to be about halfway through its life cycle. It's used about half of its fuel. So what's going to happen to it then in about another 6 billion years when it starts to run out of fuel? Well, at that point, our sun is going to be a giant star. When the hydrogen starts to run out, and that's what our sun uses to make its heat and energy is hydrogen, there's no longer a balance between pressure and gravity. The outer layers of the star start to expand. So we haven't talked about the parts of the star, but the outer layers are called the um, photosphere, which is the light layer. It's going to keep swelling up, swelling up, swelling up. It'll consume Mercury. It'll keep swelling up. It'll consume Venus. It'll continue to swell. And eventually, it'll consume Earth. It'll swell up to about the size of Mars. Now, that's not like an overnight thing. It's going to take it millions of years for it to continue to swell up to be considered a giant star. Obviously, if there's people living on Earth at that time, they won't exist. Our planet's actually going to get eaten or consumed by our sun in about 6 billion years. What happens then? Well, at that point, our star becomes what's called a white dwarf. This is a later stage in star's life cycle when the core runs out of fuel. The unstable outer layers escape into space, leaving behind the white, hot core. So basically, the inside of the sun, which is about the size of Earth, it's burning up all the fuel it has left, all the elements that make it up. It's going to continue to burn at this point, but it no longer has enough gravitational pull to hold on to the outer layers. So they just kind of dissipate, they disappear into space. And what's left behind at that point is a really, really, really hot star. Not bright because it lost its light layer, but that is a white dwarf star. Following that, and it may be a white dwarf for several million years, it'll continue to burn whatever's left, whatever heavy elements, the irons, the magnesiums it has left. At this point, it's going to be considered a neutron star. Final stage in the life cycle of some stars, when the core collapses and becomes so dense that only neutrons can exist. Neutrons or neutron stars are about the size of a city, which isn't very big. They're burning really hot, but again, they are not bright at all. So that's what's going to happen to most main sequence stars in our life cycles. But there are some exceptions to that. What about stars along the main sequence that are already pretty big stars, like the blue stars, the purple stars? They're already much bigger than our sun. What's going to happen to them whenever they start to run out of their fuel? Well, the first thing that they'll become are not giants. They will become supergiants. Late stage in the life cycle of large stars, when the core reaches high temperatures and the star's outer layers expand. So stars like Betelgeuse and Antares, those are supergiant stars because they've swollen up to enormous sizes. Betelgeuse, if we were to plop it down in the middle of our solar system, its edges would actually go out to about the orbit of Jupiter. So it's a huge, huge star compared to a lot of other stars that are out there. Sometimes, though, that's not what happens to these big stars. Sometimes, instead, what happens is those stars will go supernova. Basically, here, instead of the core slowly using up what fuel it has left, instead, it uses up all of its fuel in a relatively short time, and the core actually shrinks or collapses in on itself. And there's no gravity to hold the outer layers, and they just kind of expand or they blow up, and there's this huge explosion called a supernova. In our lifetime, no one's ever seen a star go supernova. I think the last one in recorded human history is way back in like the 500 or 800 ADs. It's been a while. But basically, what it would be like is one night we would go outside and we would see a star that looks just a little bit brighter. Next night, a little bit brighter. Next night, a little bit brighter. Maybe after 3 weeks, we go out and we see a star that's like the size of a baseball in the sky. That would be pretty phenomenal to see. And then the next night we go out and it would just be gone because it had exploded. Now realize all the stars in our galaxy are relatively around the same age as our sun. So stars don't go supernova very often because, again, the stars in our galaxy, the ones that we see, are all kind of close to the same age. There is a theoretical final stage in the life cycle of stars called black holes, which I'm sure you've heard of before. Basically, stars, as they collapse in on themselves, whether they've gone supernova or neutron stars, the material, the density of it becomes so dense that nothing, not even light, can escape its gravitational or gravity pull. Black holes are very difficult to find because they don't give off light, they don't reflect light, they actually absorb light and everything around it. So, finding these things in space that don't give off light and don't reflect light, that's very challenging for scientists to do. So, even now today, we're still, looking around and trying to figure out where exactly black holes are. So, the evidence for it is definitely not the easiest thing to find or study. So that's it for this section. Hopefully you have got enough information to fill in the blanks. Again, you could always go back and listen to it again if you missed a few before you turn in that assignment.